Okay, so the second experiment in some ways is more complicated than the first, but it starts off nice and simple. We're going to do a radioligand binding assay. Now, by convention, radioligand binding assays are plotted on a linear scale. So the x-axis we've chosen down here is linear concentration. We don't take the logs before we plot it. On the y-axis, we've got Exorcil bound expressed in picomoles per milligram of protein. So we can plot our data out, and you can see they form a nice rectangular hyperbola. Eventually, this curve would reach a maximum. We very often, though, can't put enough of a radioligand into a binding assay to directly measure the maximum binding. So we have to extrapolate the curve. In this case, you have to do it by eye. So we can draw our curve in, and then we can put in what we take to be the maximum binding. So if this curve carried on up, it would eventually reach 300 picomoles per milligram of protein. So that's our Bmax value. Bmax gives us the number of receptors in our sample of tissue here. Once we've established Bmax, we can use this value to work out the Kd. Now, the Kd is the affinity of our drug for the tissue, but it's also the concentration of drug that gives us 50% of maximum binding. So if we take our Bmax value and halve it, we get 150 picomoles per milligram of protein, and we can just draw a line across at 150 and then drop down onto the x-axis to give us our Kd value for Exorcil, and that's around about 25 picomolar. So that's the first experiment, very simple and easy to do. The next experiment is a little bit more complicated though. In this experiment, we're measuring the effect of ethanol and nicotine on demonic possession. So the experiment starts by establishing control possession in the absence of either of these drugs, and that's our 100% value. As you can see from the data in the table up here, nicotine and ethanol both increase the demonic possession. So what we've effectively got here is a concentration response or concentration effect relationship. Now, as you should know, concentration effect relationships are usually plotted on a log concentration scale. And that's because very often you deal with a very, very wide range of concentrations. So just for nicotine here, we go over a 3,200-fold concentration range, but then we would probably want to plot nicotine and ethanol on the same axis so we could compare them. And here the concentration range is even greater. We go from 1 nanomolar to 32,000 micromolar. That's a massive concentration range. The only way we can plot these data is to use a log scale. So to make the data comparable, the first thing you need to do is to convert nanomolar and micromolar into molar concentrations. And then you take the log values. So I've done that in the table down here. You can see that we've got 1 nanomolar nicotine. The log, when that's converted to molar, is -9, and that's because 1 nanomolar is 1 times 10 to the -9 molar. Similarly for nicotine, 10 micromolar becomes -5, and that's because 10 micromolar is 1 times 10 to the -5 molar. So you take the logs of all the other concentration values and you end up with the data in the table that we've got here. Once we've done that, it's quite simple. We take some graph paper, work out suitable axes, and then we plot our data out. First nicotine, and then ethanol. We can then draw smooth sigmoid curves through our data points. You can see that nicotine rises quite swiftly and then comes to a maximum at around about 200% of control possession. Similarly for ethanol, we go up quite rapidly and we reach a maximum at around about 150% of control possession. Once we've drawn the curves, we can use them to start working out some parameters that describe how the drugs behave. So the first parameter that we need to work out for nicotine is the maximum effect. Now, if this curve continued on up, it would reach an asymptote at around about 200%. So that's our maximum effect. We then need to work out the EC50 value. That's a measure of potency. EC50 is defined as the concentration of drug which gives us 50% of maximum effect. Now we're going on a scale from 100 to 200% here, so 50% of maximum effect is at 150% of control possession. So we draw a line across at 150% and then we drop down onto the x-axis. And that will give us the log EC50 value. And for nicotine, that's around about -7. So nicotine has a maximum effect of 200% and a log EC50 value of -7. We can then do the same thing for our second drug, ethanol. Again, we work out where the maximum effect is, and it's at about 150% of control possession here. And then we find the 50% value, which is in this case 125% of control possession, and drop down onto the x-axis. And that gives us our log EC50 value, in this case -3. So to summarize these data, nicotine has a higher maximum effect than ethanol, so it's a more efficacious drug, has greater efficacy, and it has a smaller EC50 value, so a more negative log EC50. And that means that nicotine is a more potent drug than ethanol. Okay, so on to the final part of this experiment. So in this experiment, we're going to plot out some inhibition curves. So this is a very common way of analysing antagonists or inhibitors. You find a control value, and then you add in your drug and see how that value, the control value, decreases with drug concentration. So in this case, we're looking at Exorcil, which is our new drug, and a naturally occurring inhibitor of redeemin, inhibitor of luciferin called redeemin. So you can see here that as we increase the concentration of Exorcil, our percent control possession goes down until it's actually totally abolished. The same thing happens with redeemin. So we've got a very wide concentration range here, and obviously that means it's best to work on a log concentration scale. So you can see that we start off with 1 picomolar Exorcil. That's equivalent of -12 when it's logged. Both drugs are on the same scale, 1 to 10,000 picomolar, so we only need one column in this table down here. So once we've established our log values, we can plot the data out. So again, work out suitable axes, log drug concentration and percent control possession. Here we're going to start at 100% and our data decrease as drug concentration increases. In fact, what we end up with is reversed sigmoid curves. So this is the one for Exorcil and then for redeemin. We can draw smooth reverse sigmoid curves through these data. There we go. And now we've got to try and characterize the drug. Now the parameter which is often used to characterize the potency of an inhibitor or an antagonist, especially when we don't know what mechanism the antagonist is working by, is a parameter called IC50. IC50 is a little bit like EC50. It's the concentration of our inhibitor which gives us 50% of our starting value, so 50% of control possession. So we can draw a line across at 50% control possession and then drop down onto the x-axis. So that gives us log IC50 values because we've got a log concentration scale here, And for Exorcil, we get a log value of minus 10.6. We can do the same for Redeemin, and the log IC50 here is minus 9.1. So what does this tell us? Well, it tells us that Exorcil is more potent than Redeemin. The parameter we're using to characterize potency is IC50, and Exorcil has a smaller IC50, so a more negative log IC50 than does Redeemin. What we can't get from this experiment, though, is any information about the mechanism by which Exorcil and Redeemin work.